audio, start video. Taylor Sunday is with us. Okay, I need to adjust that, don't I? How do I do that? Maybe like that, I don't know. I hate to foul this thing up. Maybe move this. There we go. It's not too bad. Monday, the 30th of November, 2020, Dynamics. Good deal. Well, let's see who's here. Oh, we've got a good crowd. We've got Ashley, Braxton, Ryan, Stewart, and Taylor. Good deal. We've got a good crowd. Do you guys have any questions for me? If you have a question, go ahead and ask me. This is the last week of lectures. And I hope you had a wonderful Thanksgiving vacation. We went to Chicago, so I'm kind of tired out, but I'm here. And we're studying the last topic that we have in this class, and that's impulse momentum. Studying impulse momentum. Now let's see what kind of homework we have to do here. You have a homework due, I think Thursday. It's homework number 29. And it is problem 1911. And it's due Thursday. And then we'll meet on Wednesday, the 2nd of December, and you'll have homework number 30. And it'll be due Saturday, December 5th. And that's it. There'll be no more homework. And that one is my problem 19, review problem 3, and it's due Saturday. Review, let me see if I can find that. Review problem 3. Maybe I can find that. Page 559. Yeah, there it is. It's I think the way they write it is review 19 3. Yeah. I think that's it. And I think it's due It's on page 558. And Thursday is the third, right? Yeah. Thursday, the 3rd of December. And this one's on page 558. And it's due Saturday, the 12th of December. Is that right? It can't be right. No, Saturday the 5th of December. There we go. Right, 5th of December. So that's the last two homework assignments, and then your final will be available to you. It will be available to you Monday the 10th. And it will be due that's not Monday though, no, it's the 7th. That's wrong. We'll get this right. Your final will be available Monday the 7th of December, and it will be due the 10th, which is Thursday. Thursday the 10th. And then you'll be through. Turn that in. Let me grade all those. And we'll be finished up, won't we? Yeah. Okay, well, that's where we're headed. Any comments or questions on anything? Nobody has any comments or questions. Well, I want to finish up a problem we started, I guess, a week ago, because we didn't meet on Wednesday. It was Thanksgiving holiday. This is a problem on page 548, and it is problem 1931. And I would like to do it with you because it illustrates the impulse momentum equations. Let's write those equations. We're talking about the impulse momentum equations. It's our fourth method. Remember, there are 4 methods that we use to solve dynamics problems. And you guys know those 4 methods by heart. You could rattle them off. I could pick any one of you guys. Like, for instance, Mark. Hey, Mark, unmute and say hello to me, please.
Hello.
Mark, tell the group the 4 methods of solving dynamics problems. What are they, Mark?
Well, there's Newton's second law.
Yes, that's one of them.
There's kinematics.
There's kinematics. Good going, Mark.
There's the impulse momentum, which we were just talking about.
Right, the impulse. I'm going to write those here in just a minute. And what's the last one?
The last one would be the work energy.
You've got it. That guy, he's been listening to me. He's been soaking this stuff up. Proud of you, Mark. Okay, well, let me write down the impulse momentum. Now, see, there's a linear impulse momentum. I'm too lazy to write out impulse momentum. I'll just go IM, but you know what that means. It's impulse momentum. And it goes like this. Ta-da, and there you have it. That's your linear impulse momentum equation, but there's also a rotational impulse momentum equation, and that goes like this. Goes like that. Where this is called, that is called rotational impulse. And this is called the change in rotational momentum, or some people prefer angular momentum. See, this is a rotational, and this is a linear equation. Any question on any of that? Well, okay, let's get started on this 1931 then. But I need all the room I can scrounge up. This will be on YouTube, and you guys have probably taken notes. I'm going to erase all this unless somebody says, please don't erase it. I didn't hear anybody say, please don't erase it. Okay, I'm gonna erase it. I need the room. So let me erase all that. And then we're gonna apply our rotational impulse momentum equation. Okay, this is a problem 1931. We got started on it, I guess, a week ago, and then we ran out of time. Now we have a 2-meter rod and a 0.4 meter disc. I wonder if I could do that to scale. I bet I could. I bet I could do that to scale. Meter rod. Okay, here goes. I'm going to try. I'm going to try to do this to scale. Trying to figure out a good scale. I was going to go with 20. Yeah, that might work. All right, let's try that. There we go. There's my rod. See, it's 2 meters. Well, actually, it's 20 centimeters. I'm doing this to scale. That's the way you do it when you do your stuff, right? Oh, of course, Mr. Griffin. Of course. And then we have a 0.4 meter disc. Well, now let me think now. 0.4, that'd be 4 centimeters, wouldn't it? That's the radius, right? Okay, so that would be like this. See, I'm trying to do this to scale. Okay, here we go. we're trying to draw this thing to scale. Yeah, that's not too bad. Now see what I have here is I have 4 centimeters there, and that represents 0.4 meters. And here I have 20 centimeters, and that represents 2 meters. I think, is that right? Now let me think about that. 2 meters, what I have done is I've scaled it and made it 20 centimeters. And then 0.4 meters, I've scaled it and made it 4 centimeters. You know what? I think that works, guys. So you multiply that by 10, you get 4. You multiply that by 10, you get 20. Yeah, by Jove, we've drawn this thing to scale. Like you always do your work. You do it to scale, don't you? You see, this is 0.4 meters. Now there's a bullet coming over here. Now let me draw that little bullet. Here he comes. There he comes. And he's speeding at 800 meters a second. Okay, 800 meters a second. Here comes this bullet. And they label this A and B. Okay. Here we go. Now the mass of the bullet is 10 grams, so that's 0.010 kilograms. And the disc is 5 kilograms. And the rod is 3 kilograms. Okay, well, there's all the info. Tried to draw it to scale like you're supposed to do it. Now let's get the moment of inertia of the, why don't we call it a pendulum? It's kind of like a pendulum. Have you ever seen those pendulums in the granddaddy clocks? They're kind of like that. They swing back and forth in the granddaddy clock. They don't call it granddaddy, they call it grandfather clock, right? You ever seen one of the great big things? 6 foot high, beautiful things. We'll call that a pendulum. We need the moment of inertia of it. Okay, well, here goes. Probably about A. We need the, because that's where everything's spinning about. It's rotating about A, so. Now, one way to do that is to go, for the rod, to go 1/12, 3 kilograms times 2 meters squared. But you have to use the parallel axis theorem. See, the center of this rod's right there, and the center of this disc is right there. So you have to go 3 kilograms times this distance here, which is 1 meter squared. They call that the parallel axis theorem. If you don't understand it, just speak up and I'll try to explain it. But we're not done yet. We have to do the disk. Now the disk is, oh gee. I think it's 1/2 mr squared, but let me check. In the back, it says disk is 1/2 mr squared. That's what it says. So what you do is you go 1/2 mr squared. Because see, it's rotating. It's rotating. But you have to use the parallel axis theorem. And see, what we need now is the distance from that red dot all the way up to A. Well, that's 2.4. So you're going to have to add 5 kilograms times 2.4 meters squared. It's a parallel axis theorem. Okay, now I'm going to shut up for 1 minute, and I want you to solve that, and then I'm going to call on one of my wonderful students. Okay, on your mark, get set, go, add it up. Let's see what it is. All right, I'm going to call on one of my wonderful students. Let's see, Ashley, you've helped me many times before. Tell the group what you got for the moment of inertia of this pendulum about point A. What'd you get, Ashley?
33.2 kilogram meter squared.
That's what I got. Uh-oh, I'm running out of room here. It's kilogram meter squared. Good going. Now what? Well, why don't we do that impulse momentum equation? That'd be good. And the way it goes is like this, remember? Well, now, wait a minute. We're talking about the collision now. I need to talk to you about the collision for just a minute. See, when they collide, I'll draw you artist's rendition of this collision. Here comes this bullet, and it starts to penetrate the disc. And it puts a force going to the right on the disc, but the disc puts a force equal and opposite on the bullet. Newton's third law says for every action there's an equal and opposite reaction, and these are all at the same distance going up here to the point A. Now you need to know something. The angular momentum of a body is I omega, but the angular momentum of a particle is R cross mv. I think maybe I've told you that. We could show you that in the book. See, this is the equation for a body that's rotating, but this is the equation for a particle that's moving about some point A up here. So here's point A. Okay. Well, the disk has the same distance up to A, and the bullet has the same distance up to A, and the forces are the same. What I'm trying to tell you is I think this term is going to be 0. So what you're going to have is, now you need the change here. But we need the final minus the initial. see the way it works is the total impulse is equal to the change in momentum. The total angular impulse is equal to the change in angular momentum. Well, there's your final, there's your initial. And it's going to be 0 because the forces are equal and opposite and the distances are the same for both bodies. And so the total angular momentum is 0. They have a special name for that when that happens. It's called the conservation of angular momentum. So all we got to do is write out these terms. We'll set them equal. Let me do that. The fancy name for this is the conservation of angular momentum. Uh-oh, I'm running out of room now. Conservation of angular momentum. There are no external forces disturbing this that would change the angular momentum. The forces are all internal. If you consider the bullet and the pendulum as your system, the forces between them are internal. There is no external force acting on this system that would change the angular momentum of the system. So you have conservation of angular momentum. So we'll just set these equal. Okay, well, the final angular momentum of the pendulum, well, we got the I. How about 33.2? That's the I, kilogram omega squared, plus, don't forget the bullet now. Now the bullet has a distance of 2.4 meters. That's R. And the mass is 0.01 kilogram. And the velocity of the bullet is going to be 2.4 meters times the omega. Now this is the omega immediately after collision. See, what we're doing here is we're writing this impulse momentum equation that's occurring during the collision. This is during the collision, which happens very fast, a fraction of a second. Collisions, I don't know if you've ever been in one, but they happen exceedingly fast. In a fraction of a second, blam, then it's over. The collision's over. Now, if two cars collide, bam, that collision takes place in a fraction of a second. And then you can still have motion. The cars might veer off in different directions. But see, that's after the collision. What we're writing is the equation during the collision, and during the equation, during the collision, the forces are equal and opposite between the bullet and the disc. And, well, anyway, if that made any sense, that's that term there. Now we have to subtract this term here. I don't have room. Well, we'll just put a subtraction sign here. And now I'm going to do the initial angular, what's the name of that now? That's called angular momentum. Well, it was 0 for the, wasn't it 0 for the pendulum? It wasn't moving at all. It was just hanging there. And then what was the initial angular momentum of the bullet? Well, it would be 0.010 kilograms. That's, well, I need to put my R there, I guess. The R is 2.4 meters, and the mass is 0.010 kilograms. And the velocity of the bullet was well, it's 800 meters a second. So what I've done is I've taken the final angular momentum, which I think is this. Now, wait a minute, what happened? I wrote that wrong. And this should say omega. There we go, that's better. All right, plus R cross MV. Yeah, that's right. That right there is your final angular momentum. Okay. I don't need that parentheses, do I? Probably not. And then I subtracted the initial angular momentum of my system. The pendulum didn't have any. It was just sitting there, hanging there, I should say. But the bullet did, and it had an angular momentum of R cross MV. Well, there's your R. There's your M. There's your V. And it's all equal to 0. All of this is equal to 0. Why don't we just set these equal? That's, you understand? If this is 0 and that minus that is 0, then we can just put an equal sign here, and we've got ourselves a lovely equation. And there's only one unknown in it. See it? The only unknown is that omega. Okay. Well, let's get to work and solve for that. Now, what that's going to be is the angular velocity of the pendulum immediately after the collision, which will be a fraction of a second after the collision started, because it happens fast. Okay, I'm going to shut up and do it. You do it. Let's see if we can find that omega. See if you can do it. Well, let me call on somebody. How about my friend Braxton? Unmute and say hi to me, please, Braxton.
Hello.
Hey, what'd you get for the angular velocity of that pendulum immediately after the collision?
I got 0.7596.
Well, that's not what I got. Braxton, put these numbers in your calculator and do it again. See, this stuff here is going to equal this stuff here. I'll tell you what I got. When I plug that stuff in, this is right after the collision. Let me write that. Immediately after the collision, the pendulum has an angular velocity of 0.5773 radians per second. Now, if you got that, say, uh-huh. Anybody? Anybody get that?
Yeah, I got that.
There's one. I need another one. Yeah, there's one. Give me another one. There's one. Need one more.
That's what I got.
Yeah. Braxton, did you get that figured out?
Yeah, I was scoring the first omega for some reason. I don't know why.
Yeah, that happens. Don't worry about it. Okay, well, we're doing great. Now you understand, before the collision, this bullet's moving really fast. There's a collision that happens, man, just bam, real fast, maybe 1/100th of a second. And then this thing moving. It's got an angular velocity, 0.5773 radians per second. And now what we're going to talk about is the work energy theorem. Because what happens now is, since this thing is moving, it swings up. It swings up. Now, I'm going to have to erase all this in order to have room to write my energy. Remember, there's 4 methods in this class. And one of them is the work energy method. And see, what happens is this thing's moving. And it swings up. And somewhere up here, I'll kind of fake it. I'll do a dashed pendulum like that. See, it's going to swing up like that. You guys understand that. And then it'll stop because it's moving right here, right? Immediately after the collision, it'll swing up and it'll stop. And what we're going to use now is the work energy method. The sum of all the works done on our system is equal to the change in kinetic energy of our system. Okay, well, now we have to identify any forces acting on it immediately after the collision. The collision's over, and this thing's moving. And, you know, it's got a velocity, and it's got an angular velocity. And it's got gravity. Look here, it's got gravity acting on it. What's 5 times 9.81? Let me write that down. Let's see, 5 times 9.81. You know what? It's got 4905 newtons acting from gravity there. And look at here. It's got, well, that would be 3 times 9.81. It's got 29.43 newtons gravity acting on that. And it also has a force going up here I'm not at all sure, though, that if you added those two, you'd get that force, because I think it has an acceleration. The sum of the forces is not equal to 0. The sum of the forces in this class is equal to ma, right? And I think you've got an acceleration. I don't think it's those add up to 0. Interesting. But we're interested in this equation here right now. We're interested in the amount of work done. Well, gravity does some work because, see, it goes from here up to here, and that distance is, I can figure it out. If this angle is theta right here, then you can do a little math here. This distance would be, let me think about it here. That distance would be 2.4 cosine of theta. And so the amount that disk moves up is 2.4 minus 2.4 cosine of theta. That's what this distance is right here. It's 2.4 minus 2.4 cosine of theta. If that makes a lick of sense to anybody. And the amount of work that gravity does is actually a negative because gravity is pulling down and it's going up. So the amount of work is this times 5 kilograms, well, times the 4905. That's the amount of work that gravity does on the disk, but we also have the rod. Now the rod moves from here. It doesn't move up very much, but there's a tiny distance it moves up. Can you see that? It moves up a tiny distance, and the amount of work that gravity does on the rod is minus, see this distance here is 1 foot. No, 1 meter. There you go. It's 1 meter. It's minus 1 meter minus 1 meter cosine of theta times 3 kilograms. Well, times 9.81. It's 2943. There you go. If you total up all of that, that's the total work done by all the forces acting on the system. See, this force doesn't do any work, so I didn't have to include it. It doesn't move, so it doesn't do any work. And if you add these up, they will equal the change in kinetic energy of your system. Okay. Well, what's that? We have a nice equation that goes like this. If a system is rotating about a ICZV or a fixed pivot, see, this is a fixed pivot. And we have an equation for kinetic energy about a fixed pivot. It's equal to that. Okay. Good. Now there's just one teeny thing that's bothering me, and that is our moment of inertia. We didn't include that bullet. See, the bullet's embedded in here someplace. There, I'll draw it for you. It's embedded in that disk. And it's not much. It's only 1/10 of a kilogram. Was that 10 grams? And what is this, a 5 kilogram disc? So, pretty negligible, really. Let's neglect it for right now and solve this. We know what IA is. Dang, I erased it, didn't I? Yeah, well, we had it on the board a little while ago. It was, one of my excellent students got it. It was 33.2 kilogram meters squared. Okay, so we know what it is. So we've got this equation here. No, wait a minute. Oh, God. Is this going to be plus or minus? And let me think now. Let me think and think and think. We're going to have the change in kinetic energy. So we're going to have the final minus the initial. Well, here's the problem. The final is going to be 0 because it's going to come to rest up here and have 0 kinetic energy. And you subtract the initial. That's right after collision. So there's a minus sign there. Get your calculators. You're going to have to do some algebra. This is going to take a couple of minutes. You're going to have to do some algebra to get this. Here, let me see if I can simplify it just a little bit. We could get rid of all those negatives out in front there. And why don't we do that? Well, we're going to get rid of some of these negatives. We don't need all those stinking negatives. If you got rid of it, then that makes that a plus. I'm simplifying it a little bit, but not much. And the thing is, we know what that omega is. We've got it. So here, let me put it in. We figured it out. It's 0.5773. There we go. So we made a little progress there. Wait a minute, did I forget the half? I did, didn't I? See, there's a half. I got rid of the minus signs is all and kind of rewrote it and stuck in the omega 0.5773. Okay. Well, that helps a little bit. Here, let me do a tiny bit more algebra and then we'll turn you guys loose on this. Wonder if I'm doing this right. Well, why don't I let you guys work on it? I'm going to work on it. You work on it. Here, let me make it a little nicer for you. How much room do I have down? Do I have enough? I think I have quite a bit, really. Here's what I'm getting. This is a little nicer. There. There we go. Now I think you can put all that in your calculators. I'm going to do it, and I'm going to see what I get. You do it too. Go for it. Well, I did all that, and I got I got an angle theta of 15.76 degrees. So it doesn't go up this far. 15 degrees is only about like this. .76 degrees is not very much. It doesn't go up near that far. I wonder if anybody got 15 point something degrees when they plugged in all this stuff. If you did, say uh-huh.
Yes, sir.
Yeah, there's one. Anybody else?
That's what I got.
Uh-huh.
There's another one. Well, I think that's the right answer. Let's look and see. Go to the back. This was 1931. And we'll see what they said here. 1931. They said 0.577 radians. Well, that's what we said. The book got 0.577 radians per second. And they got 15.8. We got 15.76. They rounded off 15.8. Hey, we conquered that problem. And how did we do it? Well, we used impulse momentum and work energy, didn't we? That's what we did. Is there any question on that one? Well, nobody has a question. Hopefully you're okay on it. Now let me show you one thing, and then we'll do another one. And this is on page 280. It goes back a ways. I need some room here to show you this. In your book on page 280, and the topic is angular momentum. See, linear momentum they use the symbol L in this book for linear momentum, and it's equal to mass times linear velocity. It's linear momentum. But angular momentum, they use a capital H, and it is a vector. And you'll see it there on page 280. On page 280. And for a particle, it's equal to R cross mv. Or in other words, R cross L. Angular momentum is the moment of linear momentum. You know what moments are? You know, the moment of a force is R cross F. You guys know that. That's called the moment of a force. Well, angular momentum is the moment of linear momentum. It's R cross L. See, L is linear momentum, mass times linear velocity. Angular momentum is the moment of linear momentum for a particle. Now, if you have a body, angular moment, and I think I've shown you this, it's equal to I omega. Now, you can do it about your center of gravity, or you can do it like we did in this problem about some other point. You can talk about angular momentum about any point you want to. So that's, I think I skipped telling you about this back when we were back in that chapter 15. But now I want to do another problem with you. And this one's in English. It uses slugs and feet. This is review problem 19.5. So I'm going to erase all this. Unless you say anything, I'm going to erase it. Do you have any questions? Well, okay. We're going to do, looks like a pulley. It looks like a pulley. Well, what do they call that thing? Turn to page 559. I want to see if they have a name for that thing. 559. It's a spool. Yeah, it's a spool. They have a name for it, all right. It's a spool. You've heard of spools. You know what spools are. Okay, this is review problem 19.5. And I think we got time to do it. Review problem 19.5. It's on page 559. It's a spool. It has an inner axis, half of a foot in radius. See, this is the inner axis. And then it has an outer axis that's this radius is half a foot, right? Yeah, it's half a foot, 0.5 feet, and then it has an outer radius of 1.0 feet. Okay, and they have a rope here connected to a support. And then a rope here connected to a pulley. And then somebody is putting a 40-pound force on the rope. So you know what the force is in that rope. It's 40 pounds there, and it's 40 pounds here. We'll assume that pulley is basically massless with no inertia or friction. But I'm not so sure about the rope. That's a different rope, guys. There's a rope here that's wrapped around the inner axle. This rope here is wrapped around the outside of the spool. I don't know what the tension is in that rope. We'll just call it T, okay? But I don't think you can say it's 40 pounds. It's a different rope. It's a different rope. The spool has a weight of 30 pounds. All right, let me write that down. 30 pound weight for this spool. Radius of gyration. Oh, okay. Well, we configured the moment of inertia for the spool. It's just the mass. Got to use slugs. We have to use slugs times the radius of gyration. I'm on page 559. They said it's 0.65 feet. So we can get the moment of inertia of the spool. A force of 40 pounds is applied at A. We're going to call this A for some reason. They want to know the angular velocity of the spool in 3 seconds. They're giving us the time. The time is 3 seconds. And you guys remember me telling you, if they give you time, then you want to use impulse momentum. If they give you distance, then you want to use work energy. If they give you force, then you want to use Newton's second law. Now you're free to use all of them. It's just that sometimes problems are easier in using one method than they are another method. If they give you time, it's usually easier to do the problem with the impulse momentum method. If they give you distances, they didn't give you distances, they gave you time. But if they gave you distance, like this moves so many feet, for instance, then it's easier to work the problem with the work energy, but they didn't give you distance. Now they did give you a force, and we can still use Newton's second law, and we can still use kinematics for sure. Now, let me see if I missed anything. They want to know the angular velocity of the spool in 3 seconds. Okay. Well, let's see. We got that. Somebody do that. I'm going to do it. And let's see if you agree. Go for it. Gee, I get an odd kind of an answer. I get 0.3936, maybe 34 slug feet squared. If you got that, say, uh-huh.
Yes, sir.
Yeah, there's one. So we have the moment of inertia of the spool, and we think we want to use the impulse momentum method because they gave us the time. So let's write it. Here we go. I just need some room to write it. Well, what is the impulse momentum method? Well, there's actually 2 of them. Remember, there's one that goes like this. That one is called the linear impulse momentum method. And then the other one goes like this. And that one is called the angular momentum method. Okay, so we could do both of them. That'd be fun. We'll do both of them. Let's see. This one's probably the more powerful one. So let's see what we got here. we're going to take the sum of the, they have a name for this. It's called angular impulses. We're going to take the sum of all the angular impulses on the spool. Now don't forget now, we've still got another force doing this. What did they say this was? Is that 30 pounds? I think that, yeah, that's the 30 pounds. And then we have this 40 pounds going up and a tension there. Okay. Well, now here is where you have to decide, do we want to do them about G? We could. Because that's what this is. This is about G. Do you understand? We could do that. Here, let's write it. Now, the sum of the moments about G, you probably need to put this 40 pounds going up like this. See that 40 pounds? Put it there, acting on the spool. So what we got here is, well, the 30 pounds doesn't give you a moment about G. There's G right there. Let me ask somebody. I want to make sure you guys understand. We got Jackson. Jackson, unmute and say hello for me, please, Jackson. Earth calling Jackson. Come in, Jackson. Uh-oh, coffee break. All right, let's try my friend. I've already picked on some of you guys. Shane, you won't let me down. Unmute and say hello for me, please, Shane.
Good morning.
Yeah, good morning. Hey, Shane, you see that 30 pounds that acts through the center of gravity at G? It does not give a moment. Shane, tell the group why that 30 pounds gives no moment about G.
Because it goes through G.
That's it. He understands. He understands. That force doesn't give you a moment about G because it goes through G. Ah, but this tension does and that 40 does. So let's write those. Let's see. I'm doing this equation here and I have, which way is this thing? I think it's going to turn that way. I think I'm going to write all my, angular impulses going. That's supposed to be a curved arrow. I think they're all going to curve like that. Okay, let's do that. So we got 40 pounds times 1 foot. That's curving like that. The 30 pounds, Shane told us, doesn't do any moment about G, but the tension does, only you got to subtract it, and it's at 1/2 foot. And what's it equal to? Well, it's equal to this crazy number that we cooked up, 0.39363, blah, blah, blah. Slug feet squared times omega. This is what they want. Unfortunately, we have 2 unknowns, can't solve it. But we haven't used this equation yet. This is called the linear impulse momentum equation. See this term right here? It's called linear impulse. That's the name of it. You see this here? This is called the change in linear momentum. That's the name of it. We could write it. It wouldn't hurt us any. Let's do it. All right, the sum of the forces acting on our spool. I'm going to write them. Here we go. I think it's going to go up, don't you? Yeah. This rope's coming down. Yeah, it's going to go up. So I'll say up is plus. So we have T going up plus 40 going up minus 30 going down. That's it. Times Now wait a minute. I just goofed up, guys. I goofed up major and nobody caught me. No thank you points for this. I forgot to put in my time. Shame on me. You have to multiply this by 3 seconds. Then it's equal to that. And here, you got to multiply by 3 seconds. And then it's equal to the final momentum of your spool times the mass. The mass of your spool is 32.2. And here's your velocity of your spool. Well, now that was a lot of fun, but we got another problem now. We got 3 unknowns. We have 2 equations, but we have 3 unknowns. See, we don't know t, we don't know omega, we don't know t, and we don't know little v. But there's a connection. Here's the dirty little secret. This point right here, why don't we call it point B maybe? Give it a name. It's unwinding about point B. Therefore, the velocity of the center of mass is equal to that 0.5 feet times omega, because that distance is 0.5 and it's turning angular velocity omega, and so the velocity of the center of gravity is 0.5 feet times omega, and now we have 3 equations and 3 unknowns. It could be done. You guys took algebra, but there's an easier way to do it, and let's do it that way. Instead of doing this about G, we're going to do it about that point B. And in this case here, we need the moment of inertia about that point B. Okay, well, we can get it. Here we go. The moment of inertia about B is equal to the moment of inertia about G plus the mass of the spool, 30 divided by 32.2, times the distance between B and G, which is 0.5 feet squared. Now, if you'll do that with me, we'll get the moment of inertia about B. It makes the problem a lot easier. See, B is the ICZV. Every point on that spool is rotating about point B at that instant. Okay, help me get this moment of inertia about point B. Here we go. We can do this. Well, I got an answer. I got 0.62655. Slug feet squared. Now we're going to write this equation here, and you'll discover it'll be a lot easier than doing 3 equations and 3 unknowns. So let me make some room here, and we'll do it. What we're doing is this equation right here. See this equation right here? The sum of the angular impulses about B. Okay, well, what do we got about B? Well, we got the 40. We have 40 pounds times, but see, this distance to here is 1.5, isn't it? 1.5 feet from B over to the 40, minus the 30 pounds times half a foot. Now here's what I forgot the last time. You don't want to forget the time. You have to put in the 3 seconds. See the time? Equals, it started from rest. So there's really 2 terms here. There's this one minus what you had at rest, which is 0. So all we got to do is go IB, which is 0.62655 omega. I like it. Look at this nice equation. There's only one unknown, and it's simple to solve. Go ahead and solve for the angular velocity of that spool for me, and we'll see how we did. Well, I got an answer. When I solved this, I got an angular velocity of 215.5 radians per second. If you got that, say, uh-huh.
Uh-huh.
There we go. Now let's see what the book got. This was problem, we did review problem 19.5. It's on page 559. And in the answer book, they said, they said 215. The book got an answer of 215 radians per second in the answer book. 19.5. Yep. That's what they said. 215 radians per second. We did great. We did great. Well, good for us. Do you have any questions about that one? Well, okay, that was a fun session there. We got to go over our last tool or our last method of solving problems, the impulse momentum method. And we have one more class together Wednesday at 9:30. And I'm going to, I think I'm just going to have a review session. We'll go over some of the things we've learned this semester. I think we've covered everything that we're supposed to learn. If we didn't, I'll try to mention that on Wednesday. And your final will be available a week from today. Do you have any last comments or questions? Well, okay, I'm going to push this red button. We'll say goodbye for now, and I'll see you on Wednesday at 9:30. Goodbye, students. You're supposed to say goodbye.
Bye.
Yeah, bye. Bye. See you later.